Day 109, Acoustical Engineering. Our purpose for the day is, I will learn how people design things to improve sounds. Relevance. I see strange things on the walls and ceilings of auditoriums and gyms. Success. I'll be able to point to these things in buildings and explain why they are there. Their grades for today are Homework 109. Our next quiz is not our next lesson, but the lesson after that, Day 111. Okay, the first thing we're going to do is watch a video on noise-canceling headphones.
Hey guys, I'm Jason with Sonic Electronics, and noise-canceling headphones are one of the most popular types of headphones on the market. They are ideal for environments with lots of background noise, and they give you the peace and quiet you need to get through that tough project or activity. However, few people understand exactly what noise canceling is or even how it works. So if you're curious about noise canceling headphones, then you've come to the right place. This technology aims to rid the excess ambient or background noise that prevents us from fully enjoying our music. In other words, it makes the noise level inside the headphones much more quiet so the music can be heard much more clearly. There are two different types, active and passive. Active noise canceling utilizes a power source to reduce the outside noise and is more effective at lower frequencies. They are usually more expensive because there's more technology implemented into the headphone. On the other hand, passive noise canceling uses insulation and sound-absorbing tiles and is typically more effective at frequencies above 2000 Hz and does not need a power source. Now, active noise canceling technology seeks to cancel out the background noise instead of trying to physically block it. Here's how it applies to headphones. Sound travels through the air in the form of waves, each with a particular shape. This is where the active noise canceling technology comes in. It has small microphones that detect those frequencies in a given environment. The digital processor then determines which sound waves are required to cancel the unwanted sound wave, and then it amplifies it through the headphones. To put it simpler, imagine a positive sound and a negative sound created at almost the same time. These sounds cancel each other out and bring the listener closer to a level of total silence. A good noise-canceling pair of headphones should be able to reduce the background noise by up to 80 dB, which is equivalent to about the level of a jet engine inside of an airplane cabin. Noise-canceling technology has been around for quite some time, and the technology has drastically increased over the years. As a result, there's a wide variety of noise-canceling headphones that can fit almost any application. So why should you continue living your life in a hectic environment? Pick up a pair of noise-canceling headphones today and let your ears listen in peace. I'm Jason with Sonic Electronics, your source for anything and everything headphones.
Okay, looking at the notes then. Number 1, passive headphones. Block sounds from entering your ears. Active headphones use a microphone to analyze outside noise and make opposite waves. That destructively interfere and cancel them out. Topic number 2, why do pillows and fluffy things absorb sound? Each reflection causes a material to wiggle. Each reflection in a pillow, so the feathers in the pillow or the sponge-like material in the pillow has lots of surfaces. Each reflection on those surfaces causes the feathers or the sponge, whatever, to wiggle a tiny little bit as it reflects a sound wave. This heats up the material a bit, wasting energy. This takes energy away from what might otherwise be kept in the reflection. Air molecules heat up a bit in transmitting sound. So even without reflection, sound waves lose energy and eventually die out. Number 5, soundproofing rooms have cones or triangles that make sound waves bounce a lot or reflect a lot and trap the sound waves. Topic number 3, breaking stuff. Okay, here's another video.
Trace and I live in California, and I'm gonna try to break this wine glass by only my voice.
He has the straw in there to help show that the glass is vibrating when he hits just the right note.
Mom, I broke it!
You did not.
Look it! I did! I broke a glass! I broke a glass, people!
Right now.
Look it! I broke the glass!
Stop.
I broke the glass with my voice! Isn't that just crazy? Look it!
Okay, so he was kind of lucky that the glass did not fly around in a different direction. There have been people who have reported that the glass shards have landed in their mouth, for instance, or in their eyes. So if you try to do this, please be sure that you wear protection. The idea here is similar to pushing somebody in the swing. If you push with a very small force but at the right frequency, you get the person in the swing to vibrate and to swing a very long distance. So if you sing just the right note, you are pushing at the edges of the glass at just the right moments to make it vibrate more and more and more, bigger and bigger, until the stress levels in the glass cannot be held and the thing breaks. Let's see, back to our notes. Reading the bottom part. Tap a glass and it rings with a certain frequency. This is the natural frequency. If you sing at that note, each compression wave will push on the glass at the resonant frequency and make it vibrate farther and farther each moment, just like a parent pushing a kid on a swing with tiny pushes. Eventually, the swing vibrates so much that it breaks. If you try this, get a very thin glass and wear eye protection. People have had glass fly into their mouth doing this. And you can look at these videos here if you are interested in medical uses for sound. Topic number 4, reflecting. Changes the sounds of a room. So here's another video for us to watch.
So, I have two seemingly unrelated
Fast forward here to the right time.
embark on an international research fellowship, seeking out buildings that manifested specific sonic phenomenon for the stated purpose of spiritual or transcendence experiences. I started with resonance, and that's sympathetic vibrations which create amplitude, and I don't know of a better pair of words than sympathetic vibrations. Our world could use more of it. For this, I traveled to the island of Malta in the Mediterranean, and specifically to a 5,000-year-old underground temple that was discovered under these houses in 1902. It's a 3-story temple carved out of solid limestone in the Bronze Age. And of particular interest to me was a space called the Oracle Room. Archaeologists believe that this was reserved for the shaman of this religion. The roof was painted in spiraling red paint, which they suspect might be musical notation that we can't decipher. The reason the Oracle Room was having battery issues. There we go. The reason the Oracle Room is so special is because it's a perfect resonating chamber for a specific frequency, 110 hertz. What makes it a resonating chamber? The dimensions of the space are an exact multiple of the wavelength of that frequency. So as I stood in the space, and I apologize for the lack of video, the sensitivity of the sound site meant that they patted me down and I could enter with nothing. So as I stood in the space and began to sing, searching for that tone, as soon as I hit 110 hertz, I knew it because the space came alive. Sounds suddenly surrounded you from every direction. It sounded like there were people singing with you. The intensity got so strong you could feel the vibration through your body. This is the tone of the hypogeum. So what's happening? Why does it do this? Like I said, when I start to sing, my voice travels, hits the wall and bounces back in sync with my remaining voice. Now, constantly, sound waves are interfering with each other, and they usually muddy each other up. When two waves are in perfect sync like this, it creates a natural form of amplification called constructive interference, or a standing wave. That's what created the effect that I experienced. So what? That's the sonic equivalent of an optical illusion, basically, right? And that's the exact question that a team of neuroscientists from UCLA asked in 2008 when they traveled to the hypogeum to study it. What they found was the brain, when exposed in the way the hypogeum does to that tone, experiences shifts in the prefrontal cortex and creates a functioning asymmetry within the brain. That's not dissimilar from the brain states of monks in meditation or transcendent experiences. And so archaeologists believe there's a possibility the shaman of this religion were using this chamber as a literal gateway to the doors of perception. If there's one critique of the hypogeum, it's that as soon as you stop the sound, it dissipates. For this, we introduce reverberation. Reverberation can be considered the amount of time sound lingers in a space after the source sound is gone. And for this, I traveled to the Baptistry of St. John in Pisa, 2 doors down from the Leaning Tower. Millions of people walk by it every day, and very few know what it does. A typical space such as this might have a reverberation time of 1 to 2 seconds, but because of the architecture of the baptistry, it enjoys a reverberation time between 10 and 12 seconds. I'm about to play a video with a single vocalist standing in the center of the space, harmonizing a 3-tone chord. Try and decipher what sound is coming out of her mouth and what sound is coming from the architecture around her. So if we can couple that sort of immersive reverberation with the tones of the hypogeum, we could create something powerful. But what's happening there? Why is that happening? If we take a look at the baptistry in both plan and section, the first thing you should notice is that in plan, it's a pair of concentric circles. And so as she starts to sing, her vocal energy first interacts with the inner colonnade and bounces straight back to her. If we lay this out on a timeline, we can start to map out the reflections of acoustics within the space. Some of her voice travels to the exterior wall before returning back to her. Slightly longer travel time, slightly longer reflection. Some of her voice gets trapped on the return trip between the outer wall and the colonnade, further extending that reverberation time. And this happens throughout the space, in all the nooks and crannies. Farthest traveling occurring heading straight up to the peak of the ceiling before returning back. Now keep in mind, between reflection 3 and 4, reflections 1, 2, and 3 are repeating the process over and over again. And it's this layering of sound that creates that extended reverberation time. As if that wasn't enough, a remodel to the building a few hundred years ago added a dome which encapsulated airspace, which acts as a resonating chamber, holding those sympathetic vibrations and then returning them to the space, even further extending that reverberation time. So now we've built a language of understanding on how to use architecture to make such a powerful sonic space. But how...
Okay. Let's look at our notes. The architecture of sound. What is the interference or intensification of sound by sympathetic vibrations? And the answer is reverberance or reverberation. Reverberance. The oracle's room has a diameter that is a multiple of wavelengths. So exactly one wavelength will fit from one wall to the other, and then twice the wavelength is between the walls, and 3 times, and so on. The collection of reflected sounds in a building is called reverberation. Whoops. And we saw that in the Pisa chapel. It consists of the sounds reflected off of the columns, off the walls, and the ceiling. And that causes the echo that goes on and on and on. So when we think about all of these different aspects of sound in a room, what makes a room sound good? Well, 3 basic ideas. Number 1 is, let's see here. I think I wrote something down a little bit wrong. This is reverberance. So the collection of sounds in a building, I didn't catch that, I guess. Reverberation, reverberance, is there something wrong here? Maybe you can recheck the video and find out. But I can guarantee you that's not on the quiz, so we don't need to worry about it too much. Number 11. Hearing individual voices or instruments, that's the ability of a room to have clarity. So if a room has lots of clarity, that means that the acoustics are such that you can hear the individual voices really well. Reverberance, if a reverberation, if it has lots of reverberance, then it's going to echo for a very long time after people stop playing the music. Okay, number 12. The sense that sound surrounds you is called envelopment. So that's due to bouncing off of walls all around you and getting the sound to come at you from different directions. This depends upon 3 sounds hitting in your ear. First of all, it's the direct sound, a direct line from the instrument to yourself. That's the direct sound. It hits you first. And then we have early reflections. Those are not much softer, but they just bounce once or twice. And then we have reverberations again. That word is coming up a lot here, isn't it? So the direct sound is from the music player directly to your ear. No bouncing whatsoever. And then we have early reflections that may just bounce once. And then we have reverberations where it might bounce several times, maybe down here, and then it bounces up there, and then it goes to here, and then it goes to your ear. That would be a reverberation. The acoustics of an auditorium can be measured with 3D speakers and microphones. This is a ball with 32 different microphones pointed in every direction. Music in the hall is then reproduced with a set of 30 speakers surrounding a listener. People listen and say how satisfying it is. And by this we can study the different designs of a building and see which ones would make people happier. The result is that music from the sides of the listener is most important to feeling satisfied with the sounds. So therefore architects design rooms according to when and where sound and its reflections are heard. have people here in the audience, and here is the musicians. Let's go to the musical note here. There's not much sound that is able to bounce off the walls and hit these listeners. We can have the sound come directly at them, but sound that comes this way is just going to keep on bouncing at a similar angle like that and not hit very many people. So we don't get this sideways sound that is so satisfying to people. Here, in this kind of a situation, we have the long hallway with just flat walls, and here we have it with columns on the sides, or as we see in this picture here, slats of wood. When we have a listener here and the music coming from a stage up there, it does get some of the sound to bounce off the walls to the people, and that helps, but that's just a little bit. Any other angles are going to miss them, but some does hit. Contrast that to this situation where we have these side features and we have the music playing here again. Now we get this kind of a bounce, but we also get bounces off of that, which is a slightly different time, and we have bounces that come off from the sides in that direction and bounce back. So there's many more echoes coming from the sides, and that gets to be a more satisfying sound. Next video, how sound works.
Hi, I'm John Calder of Acoustic Geometry. Let's talk about acoustics, which is basically how sound works in rooms. It may seem complicated, so let's make it simpler. Most rooms have flat walls and flat ceilings, and sound bounces off of these. So how does that affect the sound? I'll use these two Nerf guns to demonstrate. I've got this one aimed so this disc goes directly to the ear. That represents direct sound. I've got this one aimed so that disc bounces off the wall and it represents reflected sound. I'll shoot them both at the same time. Reflected sound arrives at our ears later than direct sound, even though it started out at the same time, because it's traveling farther. And this wall is only one flat surface. There are at least 6 in the average room, and that's a lot of reflected sound. But why is reflected sound bad? I'll demonstrate using these two identical patterns. The blue pattern represents direct sound waves, and the red pattern represents reflected sound waves. They start out together, but when I move the red one backwards, like a delayed sound reflection, it creates destructive interference patterns which changes the original sound wave. Here's the problem. Original sound waves are distorted by strong, later arriving reflections. Also, sound travels really fast, about 1130 feet per second. A sound wave will bounce back and forth between these two walls about 60 times in 1 second. Sound travels so fast, it fills a room almost instantly, and this is only one bounce angle. Every room has thousands. How can we make our rooms sound better? Remember our Nerf guns? I'll shoot these at the same time, again representing a sound wave bouncing off a wall. Both discs bounce together in the same direction, which means the reflected sound is at full strength. Now let's use the first of our two acoustical tools, an absorber, to reduce the strength of sound bounces. To a sound wave, an absorber looks a little like a hole in the wall, so some of the energy doesn't come back. An absorber works by reducing the strength of reflected sound that would otherwise cause more destructive interference. But if we use only absorbers in a room, it makes it sound dull and unnatural. Historically, humans don't like overly absorbent rooms. So, let's use the second of our two acoustical tools, the curved surface diffuser. It also reduces the strength of sound bounces. A diffuser works by scattering the sound reflections in different directions, smoothing out destructive interferences throughout the room. Room acoustics are greatly improved using a combination of absorption and diffusion. It's all about reducing those flat surface reflections. Use a combination of absorbers and diffusers, and your room will sound a lot more natural. Thanks for watching.
So our notes at the bottom of the page. If too much sound is absorbed, the room sounds dead. Kind of unnatural, he said. An absorber is used to reduce the strength of reflected sounds. It does this by scattering reflected sound waves. Sorry, not absorber, diffuser. An absorber sucks up the sound, prevents it from being reflected. A diffuser spreads it out, scattering the reflected sound waves. Buildings have three components that manage sound in the way they want. Reflectors reinforce sound by bouncing waves that would otherwise be wasted on the ceiling. Reflectors and diffusers reflect sound to the audience from the sides and give a feeling of being surrounded by sound. Absorbers on the back prevent echoes to the performers. These can be made of soft, fluffy material or something that looks like uncooked ramen noodles. Both have lots of spaces that sound can get into and reflect lots of times that the softer and softer with each bounce. Oop, we forgot the word hard here. In music hall, lots of reverberation makes music sound better. Tones blend more. To make a room have more reverberation, we have lots of hard surfaces. Concrete, wood, and plaster. In lecture halls, lots of reverberation makes it hard to understand speakers, little clarity. To make a room with less reverberation, lots of soft materials. Curtains, cloth, cork. They don't want too much absorbed because then the room is unnaturally quiet and our brain doesn't like that. So they have some soft materials on the wall, but not the entire wall covered. In this picture we have these giant squares, but there's lots of hard surface yet for some sound to bounce back. Multi-purpose rooms need to be able to switch modes. Multi-purpose rooms will have features that can be moved, so that they alter sounds according to whether it's going to be music or speech that's being performed. More people have mini studios in their homes as YouTube, podcasts, streaming, and other technologies grow. If you make your own studio, plan about, I forget what the number is, I think it's 40%. Yep, 40% of the wall space being some kind of absorbing panel.
We use computer simulations and calculations to predict where a building will sound before it's been built. Here you can see a computer model of a school hall. This shows in slow motion how sound spreads from the stage and bounces off the various surfaces before arriving at the audience. We run simulations to see how different sounds will be heard in different parts of the space. It's important to make sure that everyone gets a good experience of the sounds.
Remember when you had that impromptu jam session in the shower, belting out the lyrics to Like a Prayer? You know you nailed it. But then when you tried to recreate the moment with your friends during that long road trip, you were less Madonna and more Wet Cat. So if it seems like some kind of magic happens to your voice when you step into a steamy stall, that's because bathrooms usually do have some pretty wonderful acoustic properties. So you really do sound better to yourself when you sing in them. Shower stalls tend to be made of smooth, hard surfaces like tile. When sound waves hit them, they're reflected back at you rather than absorbed or dispersed. And the reflected sound amplifies your voice, basically cranking up the volume. But your voice isn't just louder. Because the various walls of your shower are different distances from your mouth, some of the sound waves from your singing travel slightly farther, so they take a fraction of a second longer to get back to your ears. And because the walls are made of smooth, hard surfaces, the waves continue to bounce around from wall to wall, so you continue to hear quieter reflections of the sound for longer than you would in, say, your living room. This effect, called reverberation, gives you the impression that the note you sang lasted a little longer than you actually held it. Reverberation can also smooth the transition between notes as the reflecting waves overlap when they reach your ear, so it's not as noticeable when you're off-key. A lot of karaoke microphones are actually designed to take advantage of this by adding reverberation electronically. Isn't that so nice of them to make sure you don't completely embarrass yourself on stage? Still, your shower performance sounds even better than your karaoke rendition thanks to another acoustic property of bathrooms: resonance, where sound waves line up in just the right way to amplify the sound. In the shower, that happens when the wavelength of a note matches up with the size of the room in a way that makes the peaks of the reflected waves line up. Lots of different notes will resonate in there, but they'll also combine with other reflected sound waves in a way that cancels out some of the sound. This effect is much more noticeable with the deeper bass tones because they have longer wavelengths with more distance between the peaks. So instead of the amplified and muted sounds being distributed all over the room, it's more like there are a few spots where your bass notes sound either a little muted or totally awesome. The acoustics in the shower are so good that recording artists sometimes use them too. Weird Al's first hit single, My Bologna, was recorded in a bathroom, and the Pixies dragged their equipment into the studio bathroom to get the perfect sound for Where Is My Mind and Gigantic. Of course, all of this means that unless you drag your crew into the stall with you, they're probably never going to hear just how beautiful your rendition of Like a Prayer can be. Thanks for asking, and thanks as always to our patrons on Patreon. If you want to help us decide what questions to answer, or
To me, this is music. To you, it's probably noise. Reducing noise, or soundproofing, is a big deal these days. So what is soundproofing? There are three categories: increasing airborne sound isolation, increasing structural sound isolation, and increasing structural mass. Let's say that water represents airborne noise. Most rooms have lots of places where noise will leak in: the door, windows, electrical outlets, air vents, and even ceiling light fixtures. Sound will leak in and out any openings in the walls, ceiling, or floor. Fortunately, there are products that are great at sealing those sound leaks, including door seal kits, acoustic window inserts, and acoustical sealants. Along with airborne noise, there's another soundproofing problem: structure-borne noise, which is sound moving through walls, ceilings, and floors. But these structures are solid, right? How can sound move through a building? We'll use a Newton's cradle to illustrate how sound energy can move through a seemingly solid wall. The first ball represents sound in a room. The next three represent a wall made up of sheetrock, framing, then sheetrock, and the last ball represents air in the next room. Watch what happens when I drop the first ball. It hits the next ball and sends energy through each ball in line. The middle three don't move much, then the energy reaches the last ball, and it moves almost as high as the first one. That represents sound energy transferring through solid structures. To reduce that energy transfer, we can place damping materials, represented by this piece of rubber, between some parts of a building. For example, between the sheetrock and the framing. With the damping material in place, the last ball doesn't move nearly as far as it did without it. This is like soundproofing between two rooms by damping parts of the structure in between. There are products that dampen structural vibrations, like RSIC clips, rubber stud isolators, floor underlayment, and elastomeric sheetrock glue. Soundproofing also means increasing structural mass, creating a denser structure makes it more difficult for sound vibrations to move through it. This Newton's cradle is the same, except we've changed the middle ball to a larger, heavier one. We're also using the same rubber damper. One ball has more mass, so this time the last ball hardly moves. There's less energy transfer through a structure with more mass. To increase the mass of your walls, ceilings, and floors, use double-layered sheetrock, build thicker framing, and use heavier, denser building materials. Soundproofing means increasing isolation and increasing mass. If you seal air leaks, dampen vibrations between structural parts, and increase the mass of building components, you'll hear a lot less noise. Thanks for watching.
Okay, so sounds that leak through small openings are called airborne noise. And we soundproof that by sealing up all the holes. Sounds moving through solids of the building are called structure-borne noise. This kind of sound is reduced by dampening material. Damping material, such as rubber. Number 32, including more mass in the materials helps to reduce sounds as well. Okay, that's the end of the notes. If you want to see more videos about different kinds of sound issues, we have the list down here.